So now we need to talk about atoms. Typical size of an atom is a little less than 1 nanometer, or 10 to the minus 9 meters. This would mean it would take several million to span a period on a piece of paper. Just remember it's very small. Now an individual atom sort of resembles a miniature solar system in some ways. It has a nucleus, analogous to the Sun, with one or more electrons in orbit around it. The electrons are a bit like planets, except they're not really hard balls like planets. We think of it more as a cloud of electrons orbiting the nucleus. The nucleus has a positive electric charge, and the electrons have a negative electric charge. And electricity is the force that binds them together. The nucleus has most of the mass of the atom, but it's very small. Most of the volume of an atom is empty space that the electrons move about in. Now, if we examine a nucleus, we find it contains several protons. It may also contain some neutrons, but we're going to talk about those later. The proton is a particle that carries 1 unit of positive electric charge. The number of protons in a nucleus determines the atomic number and determines which kind of element or chemical element the atom is. Not the number of electrons. An atom can be ionized and have more or fewer electrons. It's always the number of protons that determines what the material is. So for example, hydrogen has 1 proton. Helium has 2 protons. Carbon has 6 protons, oxygen 8, uranium 92. Every atom has to be made of one or other of these chemical elements. And there are 92 naturally occurring elements. There are a few more that have been made in physics labs, and we've organized them into the periodic table. So we have hydrogen 1, helium has 2, lithium has 3 protons, beryllium 4, boron 5, carbon 6, nitrogen 7, and so on. Understanding the structure of the periodic table is something you learn in a chemistry class. I just want you to remember that there are different atoms and they have different number of protons. The negative electrical charge on the electron is equal to the positive electric charge on the proton, and a neutral atom has the same number of electrons as protons. However, again, it's possible for an atom to temporarily lose or gain some electrons and become an ion. The nucleus is unaffected when an atom is ionized. It remains the same element. When an atom is not ionized, it is called neutral. An ion can revert to being a neutral atom by recombining with enough electrons to equal the number of protons in the nucleus. There are several ways of making ions. One way is in a fluorescent light bulb using electricity. Another is to heat gas so hot that collisions between atoms literally knock electrons off of each other. An ionized gas is called a plasma. Now on Earth we sometimes find material in the form of single atoms, but usually atoms combine together to form molecules, such as water, which is a combination of oxygen and 2 hydrogen atoms. When atoms form molecules, it's the electrons that bind together. The nucleus always stays distinct. The science of how elements interact with each other is called chemistry. The Earth's environment is particularly good for encouraging atoms to combine to form molecules. In astronomy, on the other hand, it's common to find atoms acting individually and not in molecules. It makes astronomy more simple. Now, most nuclei also contain 1 or more neutrons, and the neutron has almost the same mass as a proton but no charge. The most useful kind of helium contains 2 protons and 2 neutrons in the nucleus. We call that helium-4. Just means it's helium, meaning it has 2 protons, 4 meaning it has 4 actual objects in the nucleus. Now, a major difference between the solar system and an atom is that in an atom, an electron can only travel in certain orbits. Intermediate orbits are not allowed. The reason for this depends on quantum theory, which is one of the major theories of physics. So different electron orbits require different energies. And so On this figure, the distance of each orbit from the center represents the energy of the orbit in the electron. So the electron here can be in this orbit, it can be in this one, and 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 this one. It can't be in here. It's impossible. So to move an electron from a small orbit near the nucleus to a larger one requires you give the atom energy. So if an electron jumps from a large orbit to a smaller one, it has to give off energy. And the energy, either going in or out, comes in the form of a photon of electromagnetic radiation. Since the wavelength of a photon depends on its energy, only certain wavelengths of light can be produced as a result of electrons changing from one orbit to another. Similarly, only photons with certain wavelengths can be absorbed by an atom. Because of the importance of the energies of different orbits, we usually don't use the term orbit at all. Instead, we think of them as energy levels. These are the energies of the allowed orbits of an atom. Photons are produced and absorbed when atoms jump from one energy level to another. So for example, a photon of just the right wavelength, not any photon, it has to be just the right wavelength, can come in and strike this atom and hit that electron. That, if it's just the right wavelength, it causes the electron to jump up to the first excited state, or the next highest energy level. And eventually, it likes to be in the lowest energy level. It's going to fall back and it'll give off a photon. And one of the neat things is, as the light comes in one direction, it can go out in any other direction. Or a light of a different color can come in and have just the right energy to bump the electron up to the second excited state. And then one of two things can happen. Number one, it could go right back down to the ground state and give the same color of light off. Or it could go from the second to the first and give one color of light, and the first to the ground and give a second color of light. And so I get very distinct wavelengths of light coming out of this gas. And we can analyze it and maybe be able to determine what's in that gas. Each set of chemical elements has an entirely different set of energy levels. So each element has its own set of wavelengths that it absorbs and emits. It's kind of like a fingerprint. We can identify a gas by the wavelengths it gives out. When an atom is ionized, its ion has different energy levels than the neutral atom, so we can even determine from the light coming off of a gas whether it's ionized or not. We can separate the photons of light coming out into their different colors using a prism or something called a diffraction grating, and then look at the light coming off. And this is the basis of the science of spectroscopy, which allows us to identify different elements in the light of distant stars. So for example, if I were to look at hydrogen gas and have light being given off by hydrogen gas, I get a red wavelength, kind of this light blue and darker blues. Neon has lots of red. So if I look at, say, a neon light, I see it as red. Sodium has two strong lines in the yellow and pretty much nothing else, so a sodium light looks yellow. Mercury has this strong green in these yellows, and so a mercury light actually kind of looks yellowish green. We don't need to understand how prisms or diffraction gratings work. Don't worry about what makes the electrons jump up and down to higher levels. What I want you to know is the kind of spectrum we see here, where there are bright lines on a dark background, is called an emission spectrum. Generally, you get this kind of spectrum when you look at hot, low-density gas, such as in a nebula. If the gas density is high enough, or the emitting object was solid, we'd get a continuous spectrum instead, which we already talked about. So the spectrum of light from the sun consists of continuous emission, this continuous spectra, and looking at Wayne's law, it corresponds to a temperature of 5,800 degrees Kelvin. It has dark lines crossing it, corresponding to wavelengths of the transitions of various different kinds of atoms in the sun. The dark lines are called absorption lines, and that kind of spectra is called an absorption spectra. It occurs when light from a hot, dense region, or continuous spectra, passes through a region of cooler, lower gas, which absorbs certain wavelengths of light. So here we have the sun's absorption spectra. Notice that it kind of looks like continuous and I get all the colors, but specific lines are missing. Those specific lines we can match up to certain atoms and be able to determine exactly what elements are in the sun or a different star. The absorption line spectrum is the third type of the three main types of spectra that we need to know in astronomy. A continuous spectra has all the different wavelengths. An emission spectra has only certain discrete wavelengths. An absorption spectra has all of them missing certain ones. This is an emission spectra of hydrogen. This is an absorption spectra of hydrogen. And notice that the lines that are missing are exactly the same as the lines that are there in the emission spectra. Now the same region of gas can produce emission lines or absorption lines depending on the path of the light traveling for you. So for example, if I had a white light and I had material above it, if I had a telescope and I was looking above it, the white light goes all different directions. The light absorbs only certain wavelengths, and as they are re-emitted by the atoms, they go in all different directions, some of them which will go toward your telescope and you'll see the emission spectra. Whereas if I'm looking directly at the light bulb, as the white light comes off towards my telescope, certain wavelengths are going to be absorbed by gas, and as they come off in different directions, most of that probably won't be in the same direction, so I'll see missing light in that direction. When we look at the sun, that's what we're seeing, is an absorption spectra. So the three types of spectra to remember are continuous spectra, emission spectra, and absorption spectra. Now the next thing I want to talk about is the Doppler effect. If an object is moving towards us or away from us, the wavelength of the radiation will be changed by the Doppler effect. And you can see this or hear it with sound as well as light. So for example, if you ever have listened to a police car go by, as it's coming towards you, you hear one pitch in the siren, and as it goes away it goes down. Or that sound you hear as a car goes by really fast. It starts off at one pitch and changes as it's going away. So if something comes towards you, it has an effect of bundling up the wavelength so it sounds higher pitch, or moving away is lower pitch. So as wavelength of light becomes longer, it's called a redshift. And that happens when things are moving away from us. If it's moving towards us, it's blue shifted, or the light's shifted towards the blue end of the spectrum. So this figure shows, if I have two observers here, and the source and observers are at rest, no matter where you are, you see the same wavelength, because as the pulses of light come out, the wavelength or the crests are the same wavelength as they come out in all different directions. But if the source is moving, this large object is centered around number 1, the second circle is centered around dot 2, the third circle around dot 3, the fourth circle around dot 4. And as the light's coming off, if it's moving away, the wavelength appears larger, so that we call that redshifted. Whereas the source is moving towards you, the wavelength appears closer together, and it appears blue shifted. So if we are dealing with sound waves, the pitch of something comes towards us is higher than that something that's moving away from us. The change in wavelength of the regular wavelength is equal to the velocity over the speed of the wave. So we can use a Doppler shift to determine the speeds of stars or galaxies that are even billions of light years away from us, determine how they're moving towards or away from us.